Hey folks, estimating a population mean. I keep referring to this as 9.2. Just ignore that. We are estimating a population mean. Okay, enjoy the videos. Bye.
Hey folks, let's talk about 9.2, estimating a population mean. Okay, so um, I've drawn this picture before. There's a population of interest. We can't talk to everyone in the population, so we take a subset of that population. Hopefully it's representative of that population. Hopefully there's no bias. So we take a sample and we describe our sample with statistics, things like p hat. Remember, p hat was trying to, was a good point estimate for p. And if you take a sample, the data looks different. Maybe you get an x bar. And x bar is a good point estimate for mu. So what we learned last time in 9.1, we learned how to make confidence intervals for p hat. We said, p hat plus or minus, what was it? Z alpha over 2, p hat 1 minus p hat all over n. That was the formula we had. And then we learned how to do it in the calculator. And the whole reason we did this is because p hat is a point estimate. It's a good approximation to p. So we're going to play the whole game over because x bar is a good approximation. The sample mean is a good approximation to the population mean mu. And so our formula is just going to be x bar plus or minus. Instead of z, we now have a new formula, or new distribution, t alpha over 2, s over root n. And hopefully you watched that video that I told you to watch before this one, and that talks about the t distribution. But really quickly, so our z distribution, the normal distribution, we'd always draw a nice little bell curve. So our t distribution, and we had a whole z table that corresponded to that. So imagine if there was just a bunch of different, more squished down distributions. So maybe it looks something like that. And that would say have degrees of freedom. What's that? We'll talk about that in a second. So degrees of freedom, say maybe 1. And then let's say it got a little bit more peaky like that. That might be degrees of freedom 2. And then it's slowly getting steeper and steeper a little bit. It might look something like that. That would be degrees of freedom 3. And as the degrees of freedom increase and increase and increase all the way to infinity, it eventually turns into the normal distribution, the z. So, complicated idea. Hopefully we can see this. Ignore my highlights. You see how there's a df? That's the degrees of freedom for 1, 2, 3. And it goes all the way down. And you'll see that as the degrees of freedom, is this going to work? Oh, son of a gun. As the degrees of freedom, at the very bottom here, where you can't really see it very well, you see how it goes from 100 to 1,000 to z? Okay, and then you might recognize those numbers, 1.645, 1.96, huh? Those are our critical z values for 90 and 95% confidence interval. 2.576, our book says 2.575, this is better. Okay, we'll come back to this table in a minute. So basically every line on this table would have been a whole table. So they just gave the critical values. Okay, so everything I just said was really confusing. If it didn't make sense, no worries. We're just going to keep moving forward. Okay, pretty picture, concept. Let's try our problems on that worksheet. So we have estimating a population mean, and then the first question says, you'd like to estimate the true mean rent paid for a studio apartment in Culver City. You randomly select 15 studios. Sample mean is 1,050, and the sample standard deviation is 90. Assume rents are normally distributed. Okay, so with all these tests, there's always minimum requirements that need to be met, and I usually just throw them in there really quickly and you don't notice them. Assume the rents are normally distributed, so that helps meet the minimum requirements. Construct a 90% confidence interval. Okay, so we have our new formula, which is this one right here. I'm going to show you how to do this on the calculator also, but for right now we're going to do it once the long way. So x bar plus or minus t alpha over 2 s over root n, x bar 1050 plus or minus t alpha over 2, see that blank for a second, s sample standard deviation 90 square root of n 15. Okay, so here's a complicated idea, and right now you're just going to need to go along with it. The degrees of freedom, the df, is just n minus 1. What's degrees of freedom? Let's not worry about that right now. I'll explain it later. So the degrees of freedom is just 15 minus 1, which is 14. So they want a 90% confidence interval with the degrees of freedom of 14. So that's what I had highlighted in blue over here. So you see how I went to the 90% confidence level column, and then the row for DF14, and I see 1.761. Okay, and it's kind of hard to see, but you have your little T-table. I put it in files, 1.761. Okay. 1.761. And then we are just going to throw that into our calculators, and we just need to crunch these numbers. Found my calculator. Okay, so I would go 1.761 times 90 divided by the square root of 15. Slide out, enter. Okay, so that's my margin of error. Oh, so maybe you see that this is analogous to what we were doing before, x bar plus or minus e. Remember when we were doing the confidence intervals for proportion, we had p hat plus or minus e, so everything's analogous. So we have 1050 plus or minus 40.92. So if I add that, I get 10. I can do that in my head, I think. 90.92. Hopefully I got that right. And then if I go 1050 minus that, so 1050 minus that answer, I get 1009.08. I'm rounding to the nearest penny. So in this problem, we were trying to figure out the rent, the average rent of an apartment in Culver City, and we are 90% confident that it is in this interval. So remember, there's that one question on the last test where you had to use the very specific wording for what a confidence interval means. So is the actual average rent in this interval? Technically speaking, we don't know, but we are 90% confident that the true average rent is within this interval. And again, remember they call the lower guy the lower fence, that one the upper fence. Okay, so let's try this all again with the magic of a calculator. So we don't need to use the formula. Let's just go turn on our calculators. Can we see this okay? I wonder if I bring it up higher, if that makes it better or worse. Okay, makes it more difficult for me to see. No problem. Okay, so I'm going to go to, let's see, I want to make a confidence interval. So let's see, stat, slide over to tests, and it's the letter, you see that the letter is T, and there's only one sample, so one sample mean T, interval. Okay. One, no. Oh. what is this called? T-interval. Aha, this is just called a T-interval. So I was looking ahead when we start doing 2 groups, it'd be called 2 sample. So I wanted to call this 1 sample, but I guess I just need to remember that they just call it a T-interval. Okay. Clearly been a while since I've done this. T-interval. Hit enter. Okay. Data or stats? Do we have data, like raw data, like a bunch of numbers, or stats, summary statistics? They gave us summary statistics. They told us how many, the average, the standard deviation. Okay. So we hit stats, enter. And then it says, well, what's the X bar? 1050. What's the S sub X? What's the S, right? They're just calling the variable X. So what's the S? They say S sub X. Same thing. 90. Okay. Sample size N, 15. Confidence level, whoops. C level, 90. And then calculate that. Please work. Same answer. 1009.1. They rounded it. And 1090.9. Ta-da! So getting our confidence interval was actually pretty easy. Sweet. And then we'll just make a new video for the next one. Okay.